Hello everybody, welcome to my video about Fibonacci heap. At first, we have a short description of Fibonacci heap. In computer science, a Fibonacci heap is a heap data structure consisting of a collection of trees. It has a better amortized running time than a binomial heap. Fibonacci heaps were developed by Michael Friedman and Robert Targon in 1984. The name of Fibonacci heap comes from Fibonacci numbers, which are used in the running time analysis. Using Fibonacci heaps for priority queues, improving the running time of important algorithm, computing the shortest path between two nodes in a graph. Here's the outline of the video. At first, we have an introduction, what is a Fibonacci heap, Fibonacci heap operations with a step-by-step focus on insertion, extract minimum node, decrease key, onion, and delete. Comparison of running time with other heaps, and some experiments in Discrete performance using different priority queue based on different heaps, graphical result, and comparison of running time. What is a Fibonacci heap? Fibonacci heap, called the lazy data structure, delete for as long as possible. It's a collection of unordered binomial trees that if decrease key and delete are never called, each tree is like a binomial tree. Support merge able heap operations such as insert minimum, extract minimum, and union in constant time L1. Describe when the number of extract, min, and delete operations are small related to the number of other operations. Most fastest algorithms for computing minimum spanning trees are finding single source shortest path. Make use of the Fibonacci heap. A Fibonacci heap is a collection of heap-ordered trees. Each tree is rooted but unordered. Each node has pointed to its parent and to one of its children. Children are linked together in a doubly linked circular list. And removing a node is O1, splicing to list is O1 also in doubly linked circular list. Each node also has degree, the degree of x indicating the number of children. Each node also has mark, a Boolean field indicating whether x has lost a child since the last time x was made the child of another node. The entire heap is accessed by a pointer, minimum heap, which points to the minimum key root. Here's a sample of Fibonacci heap. A Fibonacci heap is a collection of trees satisfying the minimum heap property, that is the key of a child is always less than or equal to the key of the parent. This implies that the minimum key is always at the root of one of the trees. Compared with binomial heaps, the structure of a Fibonacci heap is more flexible. The trees do not have a prescribed shape, and in the extreme case, the heap can every element in a separate tree. This flexibility allows some operations to be executed in a lazy manner. For example, merging heaps is done simply by concatenating the two lists of three, and operation decrease k sometimes cuts a node from its parent and forms a new tree. To allow fast deletion and concatenation, the roots of all three linked using a circular, doubly linked list. The children of each node are also linked using such a list. For each node, we maintain its number of children and whether the node is marked. Moreover, we maintain a pointer to the root containing the minimum key. As you see, the minimum key here is 3. We have 3 nodes with red color that we name these nodes marked nodes. A node is marked if at some point it was a root, then it was linked to another node, and one child of it has been cut. We should know newly created nodes are always unmarked. A node becomes unmarked whenever it becomes the child of another node. We mark the fields to obtain the desired time bounds. This relates to the potential function used to analyze the time complexity of Fibonacci heap. It is a simple structure of Fibonacci heap. Each set of heap order trees that each parent is smaller than its children. Maintain pointer to minimum elements. In here, 3 is minimum. Find minimum takes 1 time. Fibonacci heap is set of marked nodes. That these marked nodes used to keep heaps flat. 26, 18, 39. We have some notation in Fibonacci heaps. N is number of nodes. In here, the number of our nodes is 14. Rank X, it's the number of children of node. For example, in here, node 3 has 3 children, so the rank of 3 equal to 3. Rank H is the maximum rank of any node in Fibonacci heap. Trees. Number of trees in heap. In here, we have 5 trees. Marks H. Number of marked nodes in heap. In this example, we have only 3 marked nodes. We have a potential function that we can have this formula. 3h plus 2 times mark h give us the potential of heap. 3 of h in here is 5, our marks is 3, so theta h is equal to 5 plus 2 times 3 is equal to 11. Operation insert works by creating a new heap with one element and doing merge. This takes constant time at the potential increase by 1 because the number of 3 increase. The amortized cost is thus still constant. This is an example. At first, create a new singleton tree. We have 21 that we want inserted to the heap. Add it to root list. Update minimum pointer if necessary. But in here we don't need to update the minimum because 21 is greater than 3. And in here the white nodes are marked nodes. They will become relevant only in the delete operation. Insert analyze. Actual cost is 1, change in potential is +1, and amortized time is 1 also. Linking operation. Make larger root be a child of a smaller root. In here, 15 is greater than 3, so 50 will be the child of 3, 3. delete or extract min. At first, we should find minimum. Operation find minimum is now trivial because we keep the pointer to the node containing it. It does not change the potential of the heap, therefore, both actual and amortized cost is constant. Operation extract minimum operate in three phases. First, we take the root containing the minimum element and remove it. Its children will become roots of new tree. If the number of children was d, it takes time OD to process all new roots and the potential increase by d minus 1. Therefore, the amortized running time of this phase is OD equal to O log n. Here's the example. We want to delete minimum, and here minimum is 3. Merge children into root list and update minimum. Consolidate trees so that no two roots have same rank. We delete 3. And consolidate the root list by linking roots of equal degree. And the kx should be less than equal of ky until every root in the root list has a distinct degree value. That for this we use as sum array. So we delete 3, so we should update the minimum. Our current minimum is 7. Root nodes are stored in the array in the index corresponding to their degree. In here, rank of 7 is 1. Our current node is 24 and the rank of 24 is 2. Our current node is 23. The rank is 0. Our current node is 17. The rank is 0. So we have the same rank into 3. Now because we have a duplicate node, we should consolidate the root list by linking roots of equal degree. In here, 23 and 17 has the same rank. So we should consolidate them, and because 23 is greater than 17, 23 should be this child of 17, like here. Again, we have a duplicate node. 17 and 7 has a rank of 2. So we should consolidate again, and because 17 is greater than 7, 17 will be the child of 7. Again, we have 24 and 7 node that they have the same rank equal to 2. We should repeat consolidate. 24 is greater than 7. So 24 is the child of 7. Okay, we're done. We go to next node, 18. Next node, 52. Next node, 41. Okay, in 41, again we face up with duplicate node. So again we should consolidate 3. 41 is greater than 18. So 41 will be the child of 18. At the end, we don't have any duplicate node with same rank. So we're done. And we find the minimum. 7 is our new minimum. First, a delete minimum analyze. That actual cost is O rank H plus O3H and at the end amortized cost after some function equal to rank H. So it's equal to log n. Delete minimum analyzed. Is amortized cost of rank H is good? Yes, it is, if only insert and delete minimum operation, because we only link 3 of equal rank. In this case, all 3 are binomial 3. The implies rank H is less than log n. So we'll implement decrease key so that rank H is equal to log n. Another operation is decrease key. Operation decrease key will take the node, decrease the key, and if the heap prepare to become violated, it means the new key is smaller than the key of the parent. The node is called from its parent. If the parent is not a root, it is marked. If it has been marked already, it is called as well, and if parent is marked, we continue upwards until we reach either the root or an unmarked node. Since the new node, it violated the minimum heap properties, so it's called and put on the node. For example, in here, at first, if heap order is not violated, just decrease the key of X. It's our mark node 26 because one child already cut. For example, we want to decrease the key of X. Change heap minimum pointer if necessary. In case 1, heap order not violated. Decrease the key of X. In case 2, decrease the key of X that the parent is 24. Heap order violated. Cut 3 root at X, melt into root list, and unmark it. If parent P of X is unmarked, it means hasn't yet lost a child, mark it. Like here, 15 goes to the root, the parent 24 is unmarked, so mark it. We mark parent P. Otherwise, if parent P of X is unmarked, mark it. Otherwise, cut P, melt into root list, and unmark, and do so recursively for all ancestors that lose a second child. X in here 35, the parent is 26. At first, we cut 35, melt it to root list. The parent of 35 was 26. 26 is marked, so we should cut 26 also and melt it to the list. "24" is another marked node that it would be the parent of node 26. So again, we should melt 24 into list and unmark it. Next, we goes to 7. Don't mark parent if it's a root, and we're done. Decrease K analyze actual cost O1 time for changing the key, O1 time for each of C cuts, plus melding into root list, and amortized cost is O1. We have some analyze. Analysis summary. Insert operation is O1, delete minimum is O log n, decrease key is O1, and we should know that the rank of H is log 1, O log 1, because the number of nodes is exponential in rank. In here we have some bounding the rank. Fix a point in time, let X be a node and Y2 and Yk denote its children in the order in which they were linked to X. We have some function rank Yi. If I equal to 1, it would be 0. If 1 greater than 1, it would be Y minus 1. And we have some improving for this function. Let Fk be the smallest possible tree of rank K satisfying property F4 and F5. We meld F4 and N5, and we have F6 now. At the end, we have a Fibonacci fact that Fk is greater than this formula, and after that rank H should be less than log n. We have union operation. Union combine two Fibonacci heaps. Representation, root list are circular doubly linked list. We have two Fibonacci heap and we do union Fibonacci. Actual cost for union is O1, amortized cost is O1 also, and change in potential equal to 0. We have operation delete. For operation delete can be implemented simply by decreasing the key of the element to be deleted to minus infinity, thus turning it into the minimum of the whole heap. Then we call extract minimum to remove it. The amortized running time of this operation is O log n. And this is our priority queue performance summary that we should some comparison between Fibonacci heap and the other heap. As you see, all the operation takes only O1 except delete minimum and delete, and n is equal to the number of elements in priority queue. Now that we have gone through the operation of the Fibonacci heaps, we can do a comparison of the time taken for this operation. For dense graphs which have many edges, the O1 amortized call of decrease key adds up to a big improvement over the theta log n, worst case time of binomial or binary heaps. And it's an concluding remarks that Fibonacci heaps are mostly of theoretical interest but are quite tedious to implement. If a much simpler data structure with the same amortized time bounds as Fibonacci heaps were developed, it would be of great practical use as well. Thank you for listening to my video.